Welcome back for another segment of the series of interviews conducted by the Department of Chemistry, University of Colombo, where we bring in the leaders of the field of science to talk about what they do and their journey to where they are now. My name is Natasha Wabitipana, and I'm a fourth-year undergraduate following molecular biology and biochemistry. Today we have with us none other than Professor Harry Gray and Professor David Beratan. To introduce Professor Harry, he is the Arnold O Beckman Professor at Caltech. He is also the founding director of Beckman Advanced Science and Technology. He has around 40 medals and awards under his belt. To mention a very few of those, he is the recipient of the National Medal of Science, the AIC Gold Medal, the Harvey Prize, and the highly prestigious Work Prize. And in addition to that, he has been presented with 20 honorary doctorates. He is the author of more than 900 research papers and 18 books. He is a pioneer in the field of bio-inorganic chemistry. Professor, it is truly a privilege and honor to have you with us. And Devinder, over to you.
Thank you, Natasha. Hello, everyone. I am Devinder Kahatapitiya, fourth-year undergraduate students following chemistry. This initiative is to inspire young minds just like ours to venture and explore the field of science, and also to give the great insights from well-established persons in the field of research. To introduce our other interviewee, it is none other than Professor David Beratan. He is the R.J. Reynolds Distinguished Professor of Chemistry at Duke University. He holds professorships in physics and biochemistry. He is also the director of Center of Quantum Coherence in SF, the Phase 1 Center of Chemical Innovation. His unique style of doing science has had a broad and deep impact on chemistry, biochemistry, and biophysics. He has developed theories with an eye towards influencing the design and interpretation of key experiments, and his impact has been tremendous. His insights and radioactive models have opened up entirely new research directions. Some of the concepts he has pioneered and developed are tunneling pathways, inverse molecular design, and chiral imprinting, and many more. So very good to have with us Professor David. We are truly honored to have you back. All of us watched the previous interview done by our colleague Srimalka, and we all are very inspired. Natasha?
Thank you.
Thank you, Devinder.
Good to be here. It's very good to be here. By the way, I had a postdoc from Sri Lanka, and her husband was from India. And they always fought over soccer and also, cricket matches. Apparently, Sri Lanka and India are very, very big rivals.
Yes, Professor.
Is that right, Natasha? Are you big rivals with India?
I mean, we are better, so we wouldn't consider as rivals. So they are doing good now. So I guess there is some competition.
Yeah, I've heard of that. So I know a lot about Sri Lanka from my postdoc.
Yes.
I call her Hima because I can't pronounce her name. It was Himamala. And she's now at Stanford. She's now a professor at Stanford. So you should look her up. She's a very young lady now who's doing chemistry, and she's at Stanford, and she's from Sri Lanka.
Definitely.
So she's a role model for you, Natasha.
Yes, Professor.
But now you've got me. Instead of her, you've got me. So you better ask me a question.
Yes, Professor. So my first question is
otherwise I'll just keep talking. Otherwise, I'll just keep talking.
Okay, Professor. So for my first question, can you tell me what science means to you and what sparked your interest to do science?
Well, science is, of course, everything to me. I love science, and I live and breathe science. I work, it's not my, I've never worked a day in my life, because if you get into science, it's also your hobby. And I can't wait for the weekends when I can work on my own problems all weekend without people bothering me and so forth. And so science means everything to me. It's my whole life, really. I got interested in chemistry when I was 11 years old because I was very interested in the colors of things, colors of grass and butterflies and the sky and everything. I was very, and so I started my own lab. I came from farming families. No one in my family had ever done any science. I don't know why I was interested, but I was. And so I built my own lab, and in one of my first experiments, I made a colored compound called the Prussian blue. I mixed up a bunch of iron compounds and cyanide, and I got this beautiful dark blue compound, which is called Prussian blue. It's a very famous compound, and I mixed these chemicals that all were sort of light colored yellows and stuff, and I mixed them together, and I got this really dark blue thing that precipitated out, and I wondered, what in the world does this color do to? So all through life, until I got to graduate school at Northwestern, I had no idea where these colors came from, but I had this burning desire to learn what the origin of color is in compounds and in nature and leaves and all sorts of things. And it wasn't until I got to Northwestern to take inorganic chemistry. There was something called crystal field theory at the time, and it explained the colors of some compounds, but it didn't explain the color of Prussian blue. So I was still not too happy, because I knew it explained the color of nickel ion in aqueous solution, the green color of nickel, and explained the blue color of cobalt chloride and a few things, but it didn't explain the colors of a whole bunch of compounds that I was interested in. So I went to Copenhagen to learn more about crystal field theory, and immediately I decided the crystal field theory was no good, because it was a terrible model. It was really a physics model. It replaced all the chemical bonds in my compounds with point charges and point dipoles. And I was very offended with this theory. And so I told my boss there, named Bellhausen, I said, I don't like this theory. I want to replace it. And of course, he liked it a lot, and he didn't want me to replace it. But I kept nagging him until he said, okay, go ahead, do something. So I don't know whether David has heard this story or not. David, have you heard of how I got into this?
I have. I think I've heard parts of it.
Well, do you want me to go on, Natasha?
Yes, please, Professor.
Okay, well, because this is how I got into the field of ligand field theory. I decided to take Robert Mulliken's molecular orbital model, which was good for organic compounds, but it failed miserably for inorganic compounds because of metals and ligands, because in inorganic compounds, there's a charge separation between the metal and the ligands. The ligands are usually negatively charged and the metal is positively charged. So there's a huge charge separation usually, and Mulliken's MO theory couldn't account for that. It gave horrible results. So what I did was I patched it up by working out the charge dependence of what we call the diagonal elements of energy for calculations. And so I patched up Mulliken's MO model for inorganic compounds by correcting the diagonal elements for charge. And a lot of people used that in the 60s. Roald Hoffman, for example, used it in all of his calculations, the stuff that I developed. And then I took the only good part of crystal field theory, which was the atomic physics of the electron-electron interactions, which allowed you to calculate the excited states, multi-electron problem. So I had this hybrid model of the physics part for the one center electron interactions, and the orbital part, which was the patched up Mulliken model. And I applied that. I decided to apply it to compounds that I was sure the crystal field theory could never account for. And they're compounds called metal oxos, oxygen atoms bonded to metals, like permanganate. Have you heard of permanganate? Potassium permanganate, well, that's one. Another one's the vanadidyline. So I started working on metal oxos because they have bonds between oxos and metals. And there is no way the crystal field theory could ever account for something like that. And so I started calculating metal oxos, and that's how I got into what is now called ligand field theory. It really wasn't called ligand field theory then. The ligand field theory caught on during the 60s, 1960s, after I had done some of this work and other folks had done similar work. And so ligand field theory became the name of this kind of MO model that was a hybrid of Mulliken's model and the physics of the atomic physics of the one center electron-electron interactions. David, does that make any sense to you?
It makes pretty good sense to me. Yeah, yeah. So you're really a theoretician at heart, right?
Well, yes.
Was,
you know, I started life as a synthetic organic chemist.
Mm-hmm.
I quickly changed to an inorganic chemist in graduate school. But I made a lot of compounds. I was a synthetic inorganic chemist, made a lot of platinum compounds. I decided to learn theory, and I did theory for 2 or 3 years.
I see. As a graduate student, or only in the postdoc?
I decided that I was a much better experimentalist than a theorist, and I would let other people like you, who are smarter than I am, do theory. And besides, I was very annoyed with the theory at the time. People were making claims about how good it was, and I thought they were ridiculous, frankly. Yeah. And so I decided that it would be better to buy liquid helium and do some good spectroscopic experiments at liquid helium temperatures than to make some lousy theoretical calculations.
Sure. Let the methods
in the 60s, David, in the 60s, the calculations were really terrible.
Right.
So I thought I could make better contributions doing experiments than continuing with theory. So I had decided to turn the theory over to other people, and in the mid-60s, I decided just to go back to my experimental work and concentrate on experiments. And so that's how I got where I was. Interestingly enough, since you said I'm a pioneer in bioinorganic chemistry, I never had a course in biology or biochemistry. I was a very hardcore inorganic chemist, a platinum chemist, a metal oxo chemist. I didn't know anything about. I didn't even know what a protein was when I was in the mid-60s. But I taught a ligand field theory course at the Rockefeller Institute in the 60s, and the people, all my students were cell biologists. And they kept coming up to me after class and saying, Harry, there's a lot of colored compounds, a lot of proteins, metalloproteins like hemoglobin and myoglobin and cytochrome C and all these. They're all colored, Harry. So they got me interested. I realized that all these proteins were colored. So I was hooked. I said, I got to find out what these colors are due to. And that's how I sort of got into bioinorganic chemistry, was with these students at the Rockefeller who showed me all these colored metalloproteins like hemoglobin and so on. So I transitioned in the mid-60s into bioinorganic chemistry. I started trying to figure out what those colors were due to, and I was particularly interested in blue copper proteins, some copper proteins like azrin and plastocyanins in photosynthesis. They're very beautiful blue proteins. If you see them coming down these columns, I mean, you would be hooked on them. They're so beautiful. And nobody knew what the colors were due to because they were very intense blue. Now, copper sulfate is blue, but it's very, very light blue. And so the intensities of these transitions were hundreds of times more than normal copper. So they weren't normal copper or inorganic copper compounds. They were some special blue copper. So that I got hooked on that. And I figured out what those colors were due to. They were due to the fact that there was a cysteine thiolate coordinated to the copper. And the transition was not what we call DD, but it was a charge transfer transition. It was a dipole allowed. And I explained that. And then I got into electron transfer chemistry, which I guess I am now known for. Of course, I didn't understand that either, and so I had to get David Beratan to explain that to me. And so I did all the good experiments, and David did all the good theory. That's basically the summary of the last David, 30 years. I've done a lot of really good experiments with my group, and David's done a lot of great theory explaining those experiments, and that's effectively why we're such good buddies.
Thanks so much,
David,
Harry.
isn't that right?
That's right, Harry. Thank you so much for that. Yeah. I think.
All right. Well, I've talked enough. Natasha, you asked me one question. I've talked to like, what, half an hour?
But it was very interesting.
You better not ask me another question.
We are not going to let you go of that easily.
I think we better ask David a question now.
Yes, I think David has a question from Professor David.
That's very interesting, Professor Harry. The same question over to you, Professor David.
Okay, well, thank you so much. My childhood was a little different from Harry's. So I didn't grow up in the countryside, I grew up in the city. So I couldn't really have a laboratory, although I'm sure I would have enjoyed having one. I could play around with baking soda and vinegar that I'd find under the sink at the house. And I grew up in Philadelphia, so we had some wonderful resources there, like the Franklin Institute. So I would go there and I would see them create artificial lightning and other amazing things. I remember a little computer built out of mechanical relays where you could play tic-tac-toe, and I thought that was fascinating. And they had a gigantic latex heart. Harry may have been through that heart at one point in Philadelphia. And
oh yeah, I've been there several times. I like that place very much. There's a lot of good things to see there.
Yeah, it was one of the first hands-on.
They have Ben Franklin's lightning rod.
That's right. They may have, and some other mechanical devices built by Ben Franklin. So this was very influential for me to see, and it was a hands-on museum. They had a telescope on the roof. You could look at images of the sun and other things. So it was an early chance to get my hands onto scientific things. Graduated from high school in Atlanta, and I was fortunate to take a summer course there. And in fact, I read one of Harry's books that summer. I think it was the Electrons and Chemical Bonding. I probably don't have the title quite right, but
no, that's the title of one of my books.
Yeah, I think that was the one we read. And as a high school student, it was very influential because I loved the laboratory work, but it taught me that there was a theoretical foundation below chemistry, behind the periodic table and so on, that could let us start to ask deeper questions about what was going on in these chemical processes. So that got me hooked on science. And for me, as Harry said, it sort of frames the way we ask questions about the world and how we understand the world. It's a 24/7 kind of occupation, and one I think we both love. So when I was an undergraduate, I had some questions that came up in classes, and I asked one of my professors, how do you explain this or that? And he said, well, we have a new theoretical chemist in the department. Why don't you go talk to him and see what theory has to say? And I got very much intrigued by the idea of calculating things and the fact that you could predict some of these phenomena that Harry has told you about, complex phenomena, colors of things, reaction rates, chemical phenomena, without ever going into the laboratory. And I was fortunate to go to Caltech. First, I guess I arrived there in 1980 when Harry had been chair of the Division of Chemistry and Chemical Engineering for a couple of years. And Harry really defined the place. I would say Caltech is a very special place. probably in the first half of the 20th century, Linus Pauling defined chemistry at Caltech. And I would say in the second half of the 20th century, it was Harry. And he was division chair when I was there. Around the time I arrived, he probably hired 4 Nobel laureates and really created this very, very special environment. So when I arrived at Caltech, what I learned was a little different from what I'd seen earlier in my undergraduate years. When I arrived at Caltech, I saw Harry and all these other brilliant scientists posing profound, deep questions. As he said, the theoretical methods of the day were not up to the questions. But the people who asked these questions weren't daunted by that. They understood that science is driven by great questions. And so I learned that. I think that was the greatest thing I learned at Caltech. It wasn't, you know, ligand field theory or theory of electron tunneling or electron transfer theory. It was the theory. It was the idea that science is all about the questions you ask and the way you pursue them with the scientific method and with this exchange between theory and experiment that Harry and I have enjoyed so much. So that's kind of how I got into chemistry, and this, you know, 40-year interaction with Harry. I think Harry was one of the first people I met at Caltech. I remember we used to take a placement exam in our first week at Caltech, and that would rattle all of us, right? We thought we were great chemists, and we'd take this exam, and it would sort of knock us back off our feet. And I remember right after that, I was standing out sort of in a daze on the campus, and Harry walked up and said, "Hi, I'm Harry Gray. Welcome to Caltech." And I thought this must be a very special guy, and we've had wonderful, wonderful interactions since. So let me stop there, and we'll.
Professor, I love what you said, that science is driven by great questions. That is something to definitely live by. And my next question for Professor Harry was going to be about your academic journey, but I think we covered more stuff about your time at Northwestern, Copenhagen, Rockefeller. Is there anything you would like to add for our viewers about your academic journey?
Well, just to say that I've been very lucky in my academic journey. I got to Northwestern just as inorganic chemistry was starting to take off. It had defined my life, really. I didn't know inorganic chemistry as a subject really existed when I was growing up because the subjects that students took in classes when I grew up were organic chemistry, physical chemistry, and analytical chemistry. These were the 3 courses in chemistry when I grew up. Inorganic chemistry was not a separate discipline when I grew up. It was part of introductory chemistry, and it dealt with things like the manufacture of sulfuric acid and things like that, where they were extremely boring stuff. So inorganic was unbelievably boring until this sort of theoretical framework came along where people could, as David said, could ask questions, could ask harder questions about bonding and electronic structure and things like that. And I happened to go to a place where there was inorganic chemistry. There were only a handful of universities in the United States where there were these inorganic chemists who were involved in what was called the Renaissance of inorganic chemistry, which occurred around in the late 50s and early 60s. And I just happened to be lucky enough to get to a place where there was such a person. His name was Fred Basolo. And I worked with him, and I realized there was this incredible field which I had sort of started in with Prussian blue and making inorganic compounds, but I didn't actually know there was all of this new stuff that one could ask in the field until I got there. So my academic journey took me there. I changed fields immediately from synthetic organic to inorganic chemistry when I got there. I went to Northwestern to do synthetic organic chemistry. as soon as I found out that there was this new wave of inorganic chemistry, I joined up, and that changed my life, really. And then when I went to Copenhagen, I changed my life again in changing the theoretical model from this crystal field model to what we call the Ligand field theory. And then I was extremely lucky to get a job at Columbia University. I didn't get the job with an application. I'd never applied. I didn't have a job there. They had read they knew about my work and at Columbia University. And when I was in Copenhagen, I got a letter from the chairman of the department offering me a job at Columbia. I had not applied to Columbia. I didn't know anybody except I knew Martin Karplus briefly, David. But I had never interviewed there. I'd never applied there, but they offered me a job because they knew about the stuff I was doing in Copenhagen, and Martin Karplus knew about it. And he suggested to the department chairman that they make me an offer, sight unseen. And I took it. And when I showed up at Columbia, I was 25 years old. I showed up as a new assistant professor. I was 25 years old. I walked into the chairman's office, whose name was Charlie Beckman, with a lot of, I had just arrived from a 44-hour flight from Copenhagen, stopped about 16 times. And I was, had all sorts of stuff with me, and I looked like, I guess, a student. And so I walked in the office, and he looked up at me and he says, "Who are you?" And I said, "I'm Harry Gray. You offered me a job." He said, "Oh yes, you're Harry Gray. I'm glad you're here. I'm gonna ask you to teach a course tomorrow." And so that's how I started. And by the way, David, the course I taught is the course in which I developed electrons and chemical bonding. Right. Yeah. I started by deciding that, okay, students should now get courses in bonding and molecular orbital theory and things like that.
It was incredibly influential.
I introduced that at Columbia, and I wrote, my first book was called Electrons and Chemical Bonding. I was very proud of it. I thought it was error-free. I was so sure it was error-free that I had a big class of students, and I said, "I'm so sure my book is perfect and error-free that I'll give any student 50 cents for. I'll give you 50 cents for every error you find in my book." 2 weeks later, I had given out $400. They found 800 errors in my book, which was a godsend to me, because then I could take all these errors, and in the second printing, I could correct them all in the second printing of the book. So I hope you got the second printing of the book. You probably, because
I believe
the book sold out immediately, and I could correct all the errors the students had found. And the second printing was, nobody has found any errors yet in the second printing.
Well, there was no book of its kind at that point.
There was no book of its kind.
That's right. So if you really wanted to understand,
so students have made an enormous difference in my life. Almost all of the work I have done has been stimulated by some student interaction. For example, I wouldn't have gotten into bioinorganic chemistry if it hadn't been for students telling me that I should get into the field, because there was something there. Essentially, everything I've ever done has been stimulated by some student discussion. I haven't figured out anything on my own yet. So students have played an enormous role in my life. And so that my academic trajectory has been essentially one of interacting with students.
I would echo that in my own scientific career, Harry. It's the student who comes in and says, you know, what you've been doing for the last 10 years is boring. You need to be doing this. And you say, oh, well, tell me more about it. or the student with the oddball insight from the lab or from the computation says we need to think about this in a different way. It's so true. It's so true.
Yeah, have you do you know about the book Harris and Bertolucci, the spectroscopy, or have you seen the analytical chemistry book Daniel C. Harris?
Yeah.
Well, the best book in analytical chemistry is one by Daniel C. Harris.
I'll definitely check that out.
So you ought to have a look at that. He was a student of mine at Caltech, this book is now in about the 10th edition. It's complete. It's the one everyone uses, I think, all over the world. And Daniel C. Harris was a student of mine, and I'll tell you about him because it's how I've always dealt with students. Daniel C. Harris came to Caltech from MIT. He was an undergraduate at MIT. He worked there with a very famous chemist called George Whitesides. And he came to Caltech as a graduate student. I didn't really know him until he walked into my office. He was a first-year graduate student. He walked into my office, and all the students call me Harry, by the way. I'm known around the world as Harry, not Professor Gray or anything like that. I'm just known as Harry. And so if you get into a chemistry conversation anyway, and you say you've talked to Harry, they pretty much know who you're talking about. That's me. I'm like Elvis or Barbara or Cher. Yeah, in chemistry, I'm Harry. So he walks into my office, he says, Harry, he says, I've decided I'm going to work with you. I'd never met him before. He walked in and said, I'm going to work with you. And I said, why? He said, well, I've talked to all the other professors here at Caltech, and they're all extremely boring. and their work is extremely boring. And he said, and quite frankly, I've looked at your work, and your work is also boring. He says, but I've heard about you, and I think you would put up with me, because you put up with a lot of students, no matter what. I said, okay. He says, okay. He says, now, I'm not going to work on any of your projects, he said, because they're all boring. Let me tell you what I'm going to work on. And he decided, he says, I know you know a lot about platinum chemistry, but your platinum projects are boring. And so he says, here's what I'm going to work on. So he went to the board and put up a project in platinum chemistry that I knew couldn't possibly work. And I said, this project will not work. You'll never make that work. And he said, I will make it work, and you're going to eat the compounds I make. I said, all right, that's a deal. So, by the way, he never made it work, but we had a great time working together, and he taught a course at Caltech called Chem 2, which he wrote a book. He was the only graduate student at Caltech who's ever been given a complete course by himself. He was such a good teacher. And out of that, he wrote Symmetry and Spectroscopy, which is a best-selling book. And then he decided to get a job in analytical chemistry at a small college called Franklin and Marshall. And he learned everything about analytical chemistry, and he wrote the book. Then he wrote the book, which is taken off everywhere. So he's really a special guy, but we had a great interaction. But just so you know that there's all kinds of interactions I've had with students. I've had to put up with a lot, but basically, I think students have to, do what they really want to do, and that's my advice to you. You should do what you really are excited about. You shouldn't do something that somebody just tells you that you need to do. You should make sure you get involved in something that you really are excited about and you love. And like David said, science is a 24/7 operation. If you're not excited about working on what you're working on over the weekend, you should go into some other field. When Friday comes around, when Friday afternoon comes around, and you think that, oh, this is great because I'm going to be able to do all sorts of other things. I don't have to do what I've been doing all week. Then you're not working on something that's interesting to you. You're working on something that's boring. Because on Friday afternoons, you should think, boy, I'm working on something. I'm so excited about what I'm working on. I can't wait for tomorrow morning so I can work on it all Saturday. If you feel that way, you're into something that you found something that you can live life with, and you will love. And that's what I found, and I'm sure that's what David has found.
Yes. No, the weekends are so wonderful.
David, you probably say, I can't wait for the weekend so I can really do some things that I really want to. I won't be interrupted.
Exactly. There are no committee meetings, no phone calls, few phone calls.
Yeah.
And so you can really sit and concentrate on what you love and push it forward. So yeah. In fact, Harry, I was interested in theory as a graduate student, but when I got to Caltech, I didn't really speak to you about research, which was probably a mistake. But of all the people I spoke to about research, John Hopfield was the guy who seemed the most excited about what he was doing. I probably didn't understand what he was doing, but I could see that among all the people I spoke to, he was the most excited, and he had the spirit that you just described, where science was everything. And he was just deeply engaged, and so that's how.
Well, I'd say you made a great choice.
Well, thank you. Yeah, he was a terrific mentor as well, and I think mentored his students in the same way that you do, right? Give them freedom to pursue problems they're passionate about, that they can make their own, and ability to pursue questions that they find engaging and compelling. And also, I think this interaction between theory and experiment that we've been talking about was a big part of the training and the environment at Caltech, right? There was always a lot of back and forth between Hopfield's group and your group. You would do experiments that would inspire our theory. We would do theory. You would tell us why it was wrong, or maybe on a good day why it was right. And I think it's important for us to emphasize what a human activity science is. You've expressed that very well, actually. But you don't just sit in a quiet room, by yourself. You interact with everyone, whether it's reading a textbook or sharing data. I remember Harry would, when I was a graduate student or a postdoc, Harry would toss preprints from his group in my mailbox at Caltech or at JPL and challenge me to explain the latest, most compelling data from his group. He would really challenge me, and it was a back and forth like this. And then we would do some theory and make some predictions, and I'd show Harry some plots, and he'd pore over them with his research group and think about how to design the next experiment to prove that we were wrong, probably. And it's an intensely interactive activity, and a very human one.
Yeah.
And
the fact is nothing has changed. I'm still sending you data.
Yeah, that's right. And vice versa. We're still sending you preprints.
And you're still telling me what it's all about.
We're trying. It's we're not always right, but that's okay. It's okay to be wrong. We don't mind.
I think the wonderful thing is when you're an experimentalist and you feel comfortable interacting with people in theory, and you can go back and forth without anyone feeling. You see, a lot of experimentalists are afraid of theorists. They don't want to be told.
You're not afraid, Harry. Well,
they don't want to be told something like this, and but I think an experimentalist who really interacts with theorists can get so much more out of the experiments. And I think the same thing is true with theorists. Theorists are willing to get in there and look at experiments without being off by themselves, just doing theory. They get so much more out of life, and they contribute so much more.
Right, and I think the impact. Right, the impact
is a kind of theoretician who really digs in and knows all about all the experiments. So that it's been a great interaction. That's why I wanted David to be on this interactive Zoom, because first of all, if he hadn't been on, I would talk all the time. And
No,
I loved
thank you,
to interact with them. This is what you're seeing here between David and me is what we do all the time together.
yeah, it's such a joy, Harry.
You're really seeing firsthand how experimentalists and theorists interact.
Right. And you know, Harry, the experiments you were doing were so beautiful and so difficult for theory to deal with, because you were working on these macromolecules with these complex transition metals bound to them. They're giant molecules, they're wiggling and jiggling, they have complicated electronic structure. And even today, they're not first principles theories that can, explain
have
everything,
a lot to
right?
learn.
Yeah, there's still a lot.
There was enormous, and of course there was enormous controversy all through this time with other experimentalists and other theorists, and you know, we were going back and forth and are having fierce discussions at meetings. There was a time where people didn't believe that electrons could tunnel, say, 20 to 30 angstroms with any kind of rate. People just didn't believe that. The textbooks had electrons moving only a few angstroms, maybe 3 or 4 angstroms in the textbooks. And so what we did was really very controversial for a while.
It was, you know, 30 years later, it all seems very intuitive and straightforward. But at the time, the most simple questions were up for grabs, right? The most foundational questions, I should say, really, were up for grabs. How, you know, how does the electron tunnel? How far can it go?
Now it's all taken for granted. It's all it's all taken for granted, and even our early papers are now never referenced because people now say that, well, this is old hat. This everybody knows this now.
But isn't that the sign of success, really, when the contributions you've made become part of the language and the fiber of the
part
field?
Of the language now.
The language, right? And we can feel good about that. Yeah, that's okay.
I remember giving my first talks on electron tunneling over 20 angstroms or so, and people in the audience expressing great doubt and saying, this can't possibly be right. And so I said, I said, it is right.
And as a theoretician, that's exactly the kind of problem you want to work on, right? Where there's you know, uncertainty about physical mechanisms and ferment in the field.
And now the questions are more: how can electrons go much further? How can they go? You know, how can they 100 times further and so forth? And then we now get into stuff that David is working on, which he has words for, like flickering resonance and that which he's developed to understand how we might be able to get electrons over, you know, 100 nanometers.
Right.
Very.
Well, it's fun to think about how the science has evolved over 40 years, right? It's gone from these tunneling reactions over, you know, 5, 10, 20, 30 angstroms to transport really over many-fold longer distances, even up to micrometers and centimeters. They're bacteria that transport electrons through their outer membranes over centimeter distances, and this influences
over centimeters now. This is the problem now has gone to this, and there's a lot of discussion now on these super long range problems, and we don't really I'd say we don't really understand this yet.
No, we don't. And
so there's still big challenges.
Yeah, right. So we were probably interested in the old days in photosynthesis and mitochondrial reactions. Nowadays, these super long distance reactions are believed to influence the global biogeochemical cycles. So they're really reactions, you know, of profound environmental consequence and interest. So you can see transitions from very fundamental questions that we may have started looking at 40 years ago to very rich, open-ended questions that persist today. Yeah.
Professor Harry, if I may, because we were talking about the electron flow, long-range electron transfers, we'd be very interested to hear about the experiment you did and the thought process behind that experiment, and if, especially in figuring out that in the proteins of respiration and photosynthesis, and also how much this knowledge has progressed at present.
Well, we got into this in the 1970s when there was people in the field of bioinorganic chemistry were arguing about whether in order to transfer electrons in proteins where the metal sites were buried fairly deep in the proteins, there were really two models. One was there'd be a big conformational change in the protein, which would put the metal site out at the surface where it could come into contact with another redox site directly. And then there were thoughts that that maybe electrons could move much further and could tunnel over these distances to get the electrons deep into proteins. And the experiments didn't tell, because the experiments were done with complexes in solution where they exchanged electrons in solution, but you didn't know what the transition state looked like. You didn't know whether there was this conformational change or not. So we decided that you had to put a probe, a redox probe, on the surface of one of these proteins, a fixed distance away from the site, to ask the question, can an electron move 2 nanometers through a protein in an experiment in which the site is an intramolecular experiment. So it's an experiment where there is no diffusional collisions or anything like that, where you don't know what the actual thing looks like at the instant of electron transfer. So you build a molecule where you know where everything are, or where everything is at the instant of electron transfer. And you build it in a protein that can't undergo this kind of conformational change. And that protein is called cytochrome C. Another protein is called azrin, which is very rigid and can't undergo this big conformational change. So we went through a whole series of possible probes: iron compounds, platinum compounds, cobalt compounds. We finally found a ruthenium compound that we could attach to a histidine at the surface, that we could build a molecule, we could build a supermolecule with a ruthenium at a histidine at the surface about 2 nanometers away from the redox site in the center. So then we had to develop a photochemical technique that would allow us to rapidly inject an electron into the probe site faster than it would inject it into the interior site. So we would build up this kinetic model where we would inject an electron into the ruthenium, and there was a driving force from the ruthenium into the iron site. So we set this experiment that we call flash quench. We developed this technology called flash quench that would allow us, first with just flash lamps and later with pulse lasers, to inject electrons or holes into a probe site a long distance from the system, and then watch the electron, literally watch the electron by absorption changes go through this protein. And what we found is, after a series of experiments, a protein could go in microseconds over 2 nanometers. And this tunneling then through 2 nanometers could be very, very rapid. And those are the experiments that we developed, this new sort of flash quench technology based on probes that we were able to put in different sites. And then in order to ask the question, how does this depend on distance? We set up this model in azrin where we could engineer histidines at different distances, put the probes on these histidines, and go through a whole range of distances from 15 to 30 angstroms, and do these experiments as a function of driving force, and get what we call the coupling limit, the rates that we could give to David Beratan, give him a set of rates that were coupling limited, that didn't have any other sort of activation factors that would muddle it up in there. So we managed to do a series of really great experiments that would give theoreticians numbers that they could really work with.
Right. These really changed the field because you could nail down where you were tunneling through, what you were tunneling through.
Yeah, so we had this really great series of experiments where we could develop what we called a tunneling timetable.